thank you, family, for coming. Because I see more friends than usually. So thank you. At least somebody came to this boring presentation about bytecode. Because we don't have a lot of time, oh, okay. We have like 50 minutes, 49. I don't know why we are coming to this talk, because it's boring. And as usual, it will be about things you don't do normally if you are a healthy, mentally healthy person. And so let's try. I'm Jarek. I work here for Allegro doing stuff, coding, after 5 years break without code. Yeah. And I'm involved in a couple of other organizations, conferences, and so on. It's not important. What is important is that I actually love JVM and love bytecode. And I would like to at some point of my life doing commercial stuff with compilers, but nobody likes to hire me for whatever reason. Okay, boring, boring, boring. Bytecode. Who of you knows how it works? Just admit it. It's okay if you don't know. I still don't know. So, what is my expectation? That after this talk, you will be like Ripley from Alien, and this will be bytecode, you know? This is you, this is bytecode. This is really fundamental stuff. There will be nothing, you know, unusual, and I will not surprise you, maybe. This is what is bytecode. And this is the first question about what this presentation is. It is about bytecode, what it is. And I remember this was discussion with one of my friends, and we came to the conclusion that this is the assembly language for not existing CPU. Okay? So, how it works. Actually, JVM, you can think about JVM as a CPU. Okay? A kind of unusual CPU. Why it is unusual? Because regular CPUs you have are register-based. So you have registers, you have accumulators, and all these kind of things. You put information into accumulators, you do the computation, you put the information back into registry, you push this information from registry to the cache, to memory, and so on. The Java CPU is unusual because it is stack-based CPU. Okay? There are a couple of hardware implementations of stack-based CPU, but this idea is not so popular among hardware people. So why, in the world of registry-based CPUs, somebody decided to create a stack-based CPU? I have just 3 slides, so you need to talk with me. Very simple reason. The problem was that when guys were creating JVM is that you have different register sizes and different amount of registers in different CPUs. So you cannot assume that you will have 4 registers, 64 bytes every time. Or you can assume that you will have 8 registers, 32 bytes long every time. So they needed to find a lowest common denominator to be able to emulate different number of registers. So they decided that they will use stack-based architecture for JVM. Okay? What it means? That everything you do in bytecode is pushed on the stack. And when you do the computation, execute method, call method, the result is pushed back on stack. And it's usual stack you know. So every thread if the Java is running in the interpreted mode, every thread has a stack. Every thread has a local variable table. So when you have something on stack and you want to remember it for future use, like assign, when you do the assignment operation, you have to remove it from stack and push it to the local variable table. And then if you want to use it next time, for example, for next method invocation, you need to get it from the local variable table and push it on the stack. Okay? Is that clear? And of course, you have the methods body. It's not actually in the thread. It's in the meta space. But what's in the thread is something called BCI, bytecode index. So this is the number, the offset of byte, but it's currently executed. Okay? So this is the stack. This is the local variable table. Okay? And the method area and bytecode index. Is it true for JVM? Only when your program is running in interpreted mode. Okay? As long as you are starting the virtual machine and it's warming up and it's profiling methods and so on, this is the way your code looks like. When you compile, when JIT compiles your code, it creates a compiled stack frame, which is different from interpreted stack frame, and the stack frame looks completely different when it's compiled. But we are talking about the interpreted mode. Okay. I told you I have just a couple of slides. You know it? Do you want to see it as a bytecode? Family. Oh, actually, I proved that I can compile my code. That's good. How to see the bytecode of your method? Actually, there's a tool which comes with the JDK. It's called JavaP. Can you see it? Yes, it's fine. And this tool does the disassembly. So it takes your class and it shows the bytecode and other things, because it's not only bytecode, what you can find in class file. I didn't pay you for this. So -c -v, it says, show me the body of the compiled method. So let's focus on this part, okay? The main method from the hello world. What you see here is all the definitions, but this is the main method. It takes this parameter, the modifiers and flags. And here, this is where magic starts, the bytecode. Okay? Actually, it's around 160, I think, instructions which are defined in the specification. Only 2 from 25 years of Java were deprecated, and 1 was added. So pretty good set. If it's stable, nothing is going to be changed and nothing is going to be removed, except Java 10, which will probably add new free bytecodes, but it's not this presentation. Getstatic, what it does. It says get the value of static field. Okay? Which static field? We'll talk about it in a moment. It's important that it gets some kind of static field, value of the static field, and it pushes it on the stack. So you have stack, and on the top of the stack, you have the value of this field. Okay? And type of this value is Java IO print stream. This is the type of this value. Now you have the second bytecode, LDC, load constant, and it pushes some value on the stack, constant value. Okay? So you have 2 things on the stack. Some object, which was the value of the static field, and some constant. Don't worry, I will explain these things. Then what you do, you say invokevirtual. So invoke the virtual method on what? On the things you have on the stack. So the thing that is at the bottom of the stack is your target, your receiver in the JVM language. So this is the method which will receive this call. And the thing after this are the parameters which come to this method, okay? So what it is? Getstatic, this is system.out, println, okay? This is, you get the value of system.out field. Then you load hello world as a parameter which comes to the function, to the method, and then you call this method. Simple. And of course, when you evoke the function, the method, the things that are on stack are just popped from the stack. They are no longer on the stack. It's empty. Unless the method returns something, then the results of the invocation is pushed on the stack, so you can use it to call next method. Simple? Simple. Whole Java interpreter. So, what are these numbers? Where I here see hello world. So this is the trick. On the beginning of the class file, you have something called class pool. This is a large table. Actually, its maximum size is 65,000. It's 2 bytes. So imagine that you actually can create a class which is too large for the compiler. If you have too many things in your class and you exceed the number of 65 things in your class, I will show you the things, it won't compile. I've seen this situation just once in my lifetime. It was the JSP code. Okay? The code, the JSP file was so large that after compilation, transformation to Java and compilation, just compiler said, sorry, oops, too large. So how the class pool looks like? It's in the beginning of the file. Do you see it? Indexes? Okay, so the class pool contains everything that is constant in your file, in your class. All the things you imported, so the classes you imported, all the method you reference, all the fields you reference, and all the hello world. See it? There is a string in the class pool, okay? And its value is hello GeeCON in this case. So whenever I say #3 in my code, it means I'm loading this value on a stack. So if you go, you will see here #3. Why class pool? For whatever reason, you need a big table in the beginning of the class, and you can reference the values directly in a bytecode. Because, sorry to say this, Java was originally designed as a platform for IoT. The first demos you will see from 94 or 5, made by James Gosling, was showing tablet running Java. It's the accident, but we have it on servers, in my personal opinion. And because at that time, the memory of the embedded devices and all these tablets was really, really small, so they need to optimize the size of the class pool, of the class file. The other thing was that there was a dream that things will communicate. Your refrigerator with your cell phone, okay? And the network at that time was really slow. So the size of the class file was important. So they say, we will compress it and use references, and we'll have a table. Special table, just reference things by index. Simple, as I said it. Okay. So the bytecode is a part of a class file. Class file is something larger, bigger. It contains more information just than your methods and your code. And bytecode is a stream, okay? So you have a bytecode, the parameters to the bytecode, to the operand. So you have operand, like invokevirtual, load constant, getstatic. And after the operand, there comes the defined number of operators. Except these things in the class file, you have the modifiers, the superclass, the class pool, the list of implemented interfaces, the list of fields, a list of methods. And this is here where you have bytecode. Okay? The class file is not bytecode. Class file is container for bytecode. And bytecode is a part just in here. Okay? Hidden. So what is in the class pool? Imported classes, method names, string, bootstrap handles. Invoke dynamic, not this presentation. Do you have Oracle database in your organization? You have it. And you have DBAs with people who should be fired immediately. And they don't allow you to add additional fields to the database, yes? They say, oh, you can't add it. So what you do usually, you create special requests and you say, okay, give me 16 fields, just in case, so I don't communicate with you next time, yeah? So you have, for future use 1, for future use 2, and for future use 3 in your database. There is something similar in the code, bytecode called attributes. With every method comes something called the attributes table. And this is the place where Oracle adds something without modifying the code, the bytecode. So bytecode doesn't change, the set of bytecodes doesn't change, but when you have annotations, they put annotations as attributes of the methods, okay? Without adding new bytecodes. They have put stack map table, they have put exceptions table, source line table as attributes. So every time they are trying to do something with bytecode and they want to be backward compatible, they are just using the attributes. Let me show you how it looks like. Because Java P also shows this. Okay, here. See it? Line number table. Without it, this is the attributes. This is not bytecode. Do you use debugger? You use it. Uncle Bob said, don't use debugger. Do TDD. You can debug your code because there is a line number table in a class file. And it says, if you are on bytecode 0, okay, it means it's line number 3 in your source file. This is the way when you will put the breakpoint in your IDE, the IDE knows that this is the breakpoint, but it should be put on this bytecode index. Because actually breakpoint is another bytecode. This is the instruction. This is how debugger works in Java, by modifying the bytecode. Okay. So this is how it looks usually. You have the operand and the operators. So if you look at the bytecode and you start to read it, you will find that what interpreter does, what Java in interpreted mode does, majority of its time it's spending on get something from variable table, push it on the stack, get something from stack, push it to the variable table. And here are the operations you have. You have a store, so get something from the top of the stack and push it to the line number local variable table. A load is the opposite operation from local variable table to the stack. Okay, you have duplication, so duplicate what you have on the top of the stack. A return, so get something what is on the top of the stack and just return it to the caller stack frame, and pop, just discard the top of the stack. Have you seen this A here? So this is the problem, one of the fundamental problems of Java. Because Java is statically type machine, virtual machine, so it needs to know what kind of variable it's storing on the local variable table. Why? Because it needs to know the size. Okay? It makes difference if you store double. It makes difference if you store int, and long. So for every this operation, you have variations of methods. You have iload for loading integers. You have dload for loading doubles. You have float for loading floats. You have astore for references, and aastore for tables. Okay? And every bytecode has variations of this. They will fix it in Java 10, maybe someday. Next, you have set of operations which are actually method invocations. You have five ways of invoking method in Java. This is the new one. It's not the new one, Java 7, okay? This is the foundation of Lambda. It is also foundation of string concatenation in Java 9. Why 4 or 5 ways to invoke method? What can be tricky about invoking methods that you need 5 ways of doing it? So down under the hood, Java is using something called single dispatch method. So how Java finds which method to invoke? It takes the receiver, so that's the thing you have on the bottom of the stack, and based on the receiver, it tries to match the method it's going to invoke. There are languages where this matching is more complex, but Java uses this really simple technique. It depends on this you are going to call this method, okay? And because it's single dispatch, what it can do is it can use something called virtual method table. So it keeps the list of all methods in a table. And there is a trick. I don't know if you noticed, Java has inheritance. Null is not the biggest mistake in our industry. Inheritance is the biggest mistake. Because how to technically work with overriding methods and the virtual calls? It's really simple. Let's say we have a class A with method 1, and we have a class B which extends class A and overrides the method 1 and adds additional method 2. Okay? Simple. So what Java does is when it's loading your code, it's create virtual table for every class. Okay? This is different, for example, from Smalltalk implementations where the virtual table was global for all code loaded in the system. And this table looks like this. On the index 0, I have a method, this is my method. When I extend something, Java takes the virtual method table from the base class, okay, and puts things on the proper indexes, okay? The trick is that if you override, the overwritten method will be on the same index. Okay? So whenever you call method at index 0, it doesn't have to do the lookup. It says, okay, it's 0. It means this method was overwritten. Okay? I will call not the original method, but something that was overwritten. This is how invoke virtual works. Okay? So what we have invoke special, invoke interface, and invoke static. Let's say we have an invoke interface. Okay? We have an interface with method, we have an implementation of this, and we have a second class which also implements this strange interface, but there is a trick. There is method 2, and method 1 is overwritten, but it's not the first method in the class, it's second method in the class. Okay? Yes, the position of the method in the virtual table depends on the ordering of methods in your code. So it means that this method overwritten will be second, not first in the virtual method table. Okay? What happens? If you call something on an interface, you can't rely on virtual method table because probably this thing will be not on index 0, but will be on index 1. So calling interfaces requires additional lookup to check which method you are actually calling. Yes, invoke interface is slower. Generally, invoke interface is slower because this is something called late binding. Yeah? And you can use virtual method table. Of course, there are optimizations and so on, but it's slower. There is a nice entry from Shipilev about the speed of invoke virtual versus invoke special. Okay. Why invoke special? Isn't it hard enough? There is something called late binding and early binding. Okay, where your virtual machine starts, there are cases where you know that whatever happens, you will be calling this method. There is no need for lookup to virtual method table. There is no need for a lookup like in interfaces, because you know nothing will be overwritten. There will be no surprise. Two cases, actually 3 cases. Case number 1, constructor. Okay? You can bind because the constructor, you know the type. It's in the type, in the call to the constructor. Okay? So you can, during the startup, say, this will be this method, nobody will overwrite me, there will be no playing with virtual table. These are the private methods, because you can't overwrite, yeah? Private. So when method is private, you don't have to do a virtual table lookup. And of course, everything you marked final. Okay? So every time you call final private method, or you call constructor, or you call super, you have to use special to omit the call to virtual table. Okay? Are you with me? Yes, you are. If you're a sick person like me, there is a brilliant, almost 60 pages about the virtual table implementations. Great thing, great reading. Really recommend for people who like compiler stuff. And at the end, in Java 7, they made it even more complex, adding invoke dynamic. Okay? What it means? Invoke dynamic is like having virtual table generated at the invocation moment. Every time. So every time you call invoke dynamic, you can actually dispatch this call to a different method. Every time. Okay? Okay. We have invoking the invocation of method. We have stack manipulation, but actually every language has something like control flow, ifs, for, while loops. I shouldn't show you the slide because this is the answer. How it's implemented in bytecode? Goto, okay? It's done with good old goto. Because, as usual, our industry didn't read. We are just reading headlines from the papers we are reading. Admit it. You read the title, and you know what's in the paper you read. And there was this famous paper that Goto is considered harmful. And people are repeating this bullshit every time. This makes me angry. Because what this guy said, he said, create tools to hide Goto from you. This is the only way you can do programming on the CPUs we have, okay? No other way of doing stuff like Goto, but you have to hide it. You don't see it. Goto is not harmful. It's just ugly. Let me give you an example. Where it is? Yeah. Okay? We have a couple of control structures here. Yeah, we have a break, we have a nice for loop. How it looks like in a bytecode. Okay? I const 0. Load 0. Okay, this is the shortcut. You could use here LDC or iload, and this is the shortcut, you know? Because usually it is 2 bytes. The instruction and the value. And because you quite often in your code use 0, 1, and 3, they created 1 byte shortcuts to save this 1 byte. This is an alias. So you're loading 0. Now you're storing this 0 in a local variable table. You load it once again. You duplicate it. And then you do if compare greater or equal. And if it's true, jump to 22, where you do this. Okay? What it is here? This is 0, 1, 2. It's actually the beginning of the for loop. Okay? Load 0 and assign the 0 to E, to I. Okay? So bytecode doesn't use your I fancy names. You spend, hours naming things, and the compiler changes it to indexes, because this is what compilers are good at, working with numbers. So this is how the control structures, and you have goto, for example. So you say you go to the bytecode here, and this is the break from the loop. So goto, it's still with us. The last thing I wanted to show you, because before I show you the tools to manipulate bytecode, because this is the things I am also going to do, is the question how exceptions work in Java. Because actually, if you look at bytecode, there is something like throw, but you will not find a catch bytecode in the instruction set. So from the bytecode perspective, you can throw exceptions, but you can't catch. So how it's solved? There is something called exceptions table, a nice structure in the attribute sections of the bytecode. Let's say we have this example with nice exceptions, just 2 exceptions. Let's see how it looks like in a bytecode. Where it is? Oh, yeah, it's here. Okay. Yeah. It's here. Every time you add exception, the compiler, the Java-C, adds this nice section, and it says, whenever there will be exception thrown between index 0 and index 26, and this exception type will be file not found exception, please jump to 29. Okay? And if you throw an exception between this one and this one index, but the type of the exception will be is IO exception, jump to 37. Okay? This is also how the finale is handled. Exactly the same way. If you see index number 29, it's here. What this A store 1 is? It's pushing the exception on the stack so you can play with it. Okay? Simple, really. Yeah. Okay. So now we have a kind of an idea how bytecode works. It's much complex when it comes to interpretation, actually execution of the bytecode. But why this mess? Why you should know it? Who uses Spring? Poor you. I'm doing it too, so I can raise my hand. It won't work without the things I'm going to show you, because Spring modifies your code. It's the same with Hibernate. Is the same with Akka, is the same with JBoss. Saying JBoss and Akka in one line. Because all these things use manipulation of your code, okay? How it is possible? Until Java 5, it was really hard. It required some wizardry knowledge about C++ and Java management interfaces. You had to hook into running machine with the C process and play with these things. But in Java 5, they added something called agent, Java agent. So you can write in Java code which modifies your bytecode in Java. Java in Java. How it looks like. You have to create a jar file with the manifest, and in this manifest, you will have a pre-main class. Not the main class, like usually you have in your jars, but pre-main class. And this is your own code, okay? Next, you have to actually implement this class. And this class, it doesn't extend anything, but it has pre-main method. Not main, pre-main. And this is a kind of arguments you can pass to agent. Where is the trick? Instrumentation. This is the only way you can get the instance of this object. Just by this. You can't instantiate instrumentation. No. The JVM gives you injects the instrumentation for you. And this class has a nice method called addTransformer. Optimus Prime. What the transformer does, every time you load class, before the class will be instantiated, and before the class will be verified by the verifiers, the code of this class is pushed to the transformer. The transformer can do anything you like with your code, returns back the new bytecode, and the new bytecode, the modified bytecode, is actually verified and loaded into virtual machine. Okay? This is how, for example, runtime waving works. And this is the example code, the transform method. So this is, where is the, this is your bytecode, your class, actually, not the bytecode, the class, as a table with bytes. And if you have right tools, you can modify it and change the behavior of your code. And this is how you run it. You create this jar and you say minus Java agent, the name of the jar, and then everything, not everything, actually things from the bootstrap class loader. In some cases you can do it, but normally you won't be able to modify JavaLang object or JavaLang string. Yeah? Okay? So you get classes which are on the application class path, class loader. I think it will change with Java 9, but yeah. How to do it? Yeah? Because we won't be modifying bytecode with bare hands. We are humans, we are lazy. So there are tools to do it. I have 12 minutes, so probably will show you 2 tools, but I think it will be enough. There's one thing called ASM, and it's really low-level thing, and it's actually now part of JDK. It's hidden because it was used by the guys writing Nashorn. And I've heard rumors about adding ASM as an official part of the JDK and so on, but just rumors. And you can modify your bytecode or generate new bytecode with ASM. Yes, I'm using Eclipse. Shut up. Yeah, boo, boo, boo. Yeah. Unfortunately, the code compiles with Eclipse the same way. I'm too old to waste my time, learning another IDE. So, quick thing. You get hold of the class writer, so this is from the ASM, and it can generate your code. You say that it's based on the visitor pattern. So you say, actually, I want to generate Java 1.7 compatible bytecode, and this class will be public. This will be the class name. This will be the annotations. Of course, you have to explicitly, at the compiler level, you have to say that you superclass JavaLang object. You want to do it in the code because Java-C does it, but when you generate, you have to remember. And this is the list of interfaces implemented by this class. Do you see it? In Java, we use dots to separate packages. In JVM, we use slashes. Because as usual, there were 2 teams, And they weren't talking to each other. So yeah, this is Java lag. And then you say generate method. The constructor actually is a regular method. The only difference is that its name is init and its return type is void. So what we do here, we generate public constructor which accept the integer as a parameter. And when we have this method visitor, we can actually visit code. Okay, so generate code as we go. It's pretty simple. What this method does is load 0. What load 0 does in a method or constructor? It pushes this on stack. Remember, you had at the bottom of the stack, you will always have receiver. So 0 is always your this. If you see it bytecode load 0, it means if the method is not static, I'm going to do something on this. So what I do here, I load this, and then I will call invoke special. What is this? It's the super call. Okay, I call super constructor of the Java lang object type. Then I load the parameter. So this is this parameter passed to this constructor. I store this parameter, load it once again, and I called invokevirtual to string. What it does, this code, it's actually printing the value of the integer you pass to the constructor. Should I prove it, that this code works? Yes, will do. Oh, come on. Okay. This is where I generate my class. I'm loading this class. I get the constructor and call the constructor. Of course, if you say I recorded this, I will change this. Okay? Clear? Kind of, yeah? As you see, ASM is pretty complicated, because you still operate at the bytecode level. There are better tools, and one of my favorite is ByteBuddy, definitely. There is Java Assist, which is actually no longer actively maintained, I think. There is a CGLib, which is full of memory leaks and problems with generated code. There is BCL from Apache, which is actually not able to generate above 1.4. One thing I would like to show you, which has some practicality, is Byteman. Okay? What is Byteman? This is things that you shouldn't tell to your people, but you're actually using it, but it saved my ass a couple of times. This is a tool from JBoss. And I actually used a lot of it with JBoss, and you can use it with any code, okay? Because it's from JBoss, doesn't mean you have to use JBoss with Byteman. What it does, it allows you to connect to running machine and modify your code. And when you disconnect from this machine, your old version of the code will be bring back. Imagine what you can do on production. You don't have to restart your machine. You just load, modify code, profile it, disconnect, and everything is fine. The trick is that if you want to Byteman to be installed on your machine, you have to send it to your infrastructure people, but remember, change the name of the file. Because people from infrastructure know Google, and they will check what you are trying to load in the production. Yeah? So I usually call it important.zip. And we say, guys, this is some kind of batch job, we need to run it. Oh, of course, no problem. Because they are too lazy to unzip it, but not such lazy to check in Google what Byteman is. You can write rules, okay? This is not the presentation about Byteman, but you can say, but I have a rule, the name of the rule is trace file, and whenever you find the file processor class, and whenever you find the method is called, so the process file method on file processor is called at entry. So when you enter the method, please print out the name of the first parameter of this method. Okay? Let me show you the example. 5 minutes, it's okay. So what I'm doing, I'm running my process using BM Byteman Java. This is a simple wrapper shell script, nothing fancy. And I'm just running the application which reads the content of the file and prints the number of lines in this file every few seconds. Okay? And I run it under the BM Java wrapper. What it does is actually just adds the Java agent switch to running machine. So this is my code running, and it's saying I have a file which has 158 lines of code. And now I'm going to modify behavior of this machine, not touching it, actually. Because what I will do, I will go to the next console, and I will run script called bm submit, okay? And I will just give the reference to file with my rules, okay? Something happened. I'm just printing the name of the file. I was not restarting in the background this process. This is still the same process. Imagine what we can do. We are debugging actually bugs and finding bugs in JBoss 4.2 in Transaction Manager because we had a problem with the connections from the JDBC pool not returning back to the pool. And it always, as usual, were happening on production only. So we wrote a simple rule that on every time we say checkout and borrow on the connection pool, we print the arguments. We find out what's going on. What's fancy, even more, there are some additional scripts that come with Byteman. If I start this process once again, okay, and I run the submit with somewhere over the rainbow. With the file monitor script, which comes as a sample from Byteman, it prints out, every time you close and open the file, it prints out the stack trace. So for example, you can find which of your brilliant piece of code opens the file from which method, from which thread. You can not only do simple printing of the things that are going, you can also mess with the body of the method, modify it, okay? It's not good. Hacking tool. 2 minutes. Okay. Questions?
I have a question about the Byteman.
Huh?
So all this stuff goes to standard output, or is there any way to put it to the log file or something like that?
You can write it to a file, so you can run a Byteman with the name of the output file. What's funny is you can also submit the script from the remote machine, because you can run Byteman with the open port, and then you can connect remotely and push the rules remotely. So anything. There are things you can do. Excuse me? Yes, in the new version of Byteman, you can have protect this port. Yeah. And yes, there is an overhead in one moment when you start the machine, because there is even if you don't have the rules installed, okay, it's this additional step that the transformer needs to get your code, even if it's not doing something. So it starts slower, a little bit slower, but runs as usual code. And what's funny, if you submit this rule, it will be JITed. So it's treated as a normal code. Yeah?
Have you ever seen generated bytecode by a compiler? Here I am.
Yeah.
Such bytecode that was generated inefficiently. So when you looked at it, you kind of thought, well, I have to change it. then you change it and it performed better.
No.
That does it happen or may it happen?
It doesn't happen because at the end of the day, you have JIT.
Even on the older compilers?
Yes.
You know, because I have heard about some people that are complaining about some implementations of JVMs and compilers that are sometimes doing really weird stuff that can be handwritten to achieve better performance.
I don't see a much connection between the quality of the generated bytecode. Okay. Of course, if you are running in the interpreted mode, yes, and if you're, for example, you have code which is not hot, so it won't be jitted. This can have impact, sure, but I haven't seen much improvement if you modify or try to do bytecode better. Yeah. So thank you.